remove the protection.
Yeah, just remove the protection that will be covering the microscope. That's only to avoid to have dust, for example, in the optics of the microscope. So when we finish, we just cover it to avoid dust from the air. And now to turn it on, it's always these switches here from left to right. So
Left to right.
first you press PC microscope and wait a little bit because you know that the microscope is doing some initialization, yeah. By the way, all the steps are here, so you can just follow. Turn on green PC, then scanner power, which is the next one. So this is always here.
Do you have wait the initialization finished?
Yes, so exactly. So from left to right, I'm waiting a little bit between the different steps just to let the microscope do his own thing. So first PC, wait a little bit, scanner, wait a little bit. When there is no more noise, then you know that you can go to the next step. Next is the laser power. It's written there if you forget, but it's very easy, it's just this order. And finally, the laser has a key also, it's like 2 buttons. Just laser power and then on. That's just to turn.
Is this a very dangerous system?
No, it's not a very dangerous, it's just that the lasers have a short life. I mean, if you leave them on for a long time, they will, the light will finish, you know. So it's just to, I mean, you have to be careful because they are lasers, so you shouldn't look very directly at them. But these lasers we have in this microscope are not, they are type, there are different types. This is type 1, and I think the one in the Raman is like type 3. That's dangerous, and that's why we have a protection that we put here in the microscope. So every time that we are measuring, we have a dark protector around. But this one is not as powerful as the other one, so this is fine. Then in this computer, we usually have, each user has his own account, so I have to create yours. For today, we will use mine. So you will log in with your user and password.
Yeah.
And then the software we're going to use for getting the images is this one, LAS AF. So double click. And it now takes a while, and then it asks you a couple of things that you just have to press OK, but we will look at them, and then we're ready to go. So the first thing that it asks is about the configuration. We use the default configuration, so just press OK. Just so you know, here you can change different configurations, but we use the default of machine one, so just press OK. And the next question will be, can I initialize the stage so it will calibrate the position, because then we will change the X, Y and Z coordinates with this kind of joystick. So it has to be calibrated so the limits are established. So that's the next thing that it's going to ask. This is a little bit slower. This step that is almost done. It's, as you see, initializing different things. And then it asks, can I initialize the stage? In this case, this step asks you because it's going to move the platform. So the other things, it can do it on his own. But now he's asking because it's going to move the platform. So you have to make sure you don't have a sample there or whatever. So just confirm, saying yes. And now it's going to go up, down, right, left, and calibrate the position. turn it on, it's very easy. First here, all the switches from left to right, then software, OK, and yes. It can't be easier. And also you have all the steps here. Have you done any microscopy before? The optical microscopes or anything?
No, nothing.
No, you're not very familiar with microscopes in general?
No,
or?
I'm not.
Okay, so I will also explain you the different types of objectives we have. First of all, I'm going to put this down. So this is the most important thing that you have to be careful about. Well, these and the lasers. These do not damage the objectives. So every time that we are going to put a new sample or something, the best thing is to put the platform down as much as possible. So we have so we have space here to operate, move the sample, and don't hit the objectives. This
Heat of the objective.
It has happened before.
Sorry,
that
Laura,
yeah.
do you want to use here?
Not today.
Can I do it today?
Sure. So I was just bent in to put the cryostage on, but if you're going to use it today.
I'm going after I have 4 samples.
Okay. So I didn't even check the diary. Were you booked? Okay. Sorry. So it's just bent it, but then do your thing and I will change it.
I will change it.
I can do it. Don't worry. Bye. Okay, so the important thing is not hit the objective, because it has happened that some people are not very careful and you have your slide with the sample, and if you don't have enough space, if for example the platform is very close, when you move the objectives, each objective has a different length.
Yeah,
Exactly. Maybe you are working
Too
with
close
this
and
one that has a long space, and then you move this one, and if it is very close, maybe you hit the objective, and it can break the parts that are
lens or
exactly. So the most important thing is to be careful. Always have enough space to move the samples and not hit the So this is up and down, this one, so it's the same direction, and then with these other two you have left and right. Do you also want to try? Just to maybe it's a bit less boring if you actually touch it. This one is, I don't know which one is right and left, and but it's actually X and Y. These two move in this direction, and then with this you can go up and down. And also you have fine and coarse. The difference of these two is when you are in the coarse, so if you press here, for example, it goes very fast.
Oh, okay.
And if you press fine, it goes really slowly. Even if you go fast, it goes very slowly. So, for example, to go down, you want to go down fast. So you press coarse and then go down as much as possible. But then when you're focusing the sample, maybe you're already very close to the focus and you want to be very accurate, then you can press fine and move the focus more precisely.
It's very difficult. No, I mean difficult to find the focus.
You see, it's not so difficult. You'll see. You have the same for this is for the Z, which is the focus, and the XY. These two have also a fast and precise.
But this two is for this two.
Yeah, it says XY.
Oh, okay, XY.
Yeah, XY. So it's these two that move in the X and Y axis, let's say, or coordinates. This is the Z. So this is the focus. Now it's in fine, so it moves very slowly. But if I press coarse, it will move faster. You see? Okay. So the types of objectives, we have two types. These three objectives are air objectives. So you don't need to put any oil or anything to work with them. You just put the sample here and observe it. These two at the back are oil immersion objectives, which means that you have to put your sample, then a drop of oil, and immerse the objective in the drop of oil. We will see when you have the samples, and this will increase the resolution. So because these are higher magnification, we go from 5x Then we have 10x, 20x. These are not very high magnifications. We don't need a really good resolution. But when we go up, for example, to 63x, that is the maximum magnification we have, then we need to use oil, and this will change the refractive index of the path of the light that goes to the objective will be reflected in different ways because it has oil, so the resolution will be better, basically.
Okay.
So one thing to be very careful with is not to put oil in the air objectives. So we always go in this direction. If you want to start at low magnification, you put the sample here to more or less focus it without the oil. Then if you want to increase a little bit, you go to the 10x, you can go to the 20x, and then if you want to go higher, you go to this empty space. You will have your sample here. You put a drop of oil here in the open space. We don't have any objective in the middle, so we won't hit anything. So you put the drop and then move this, and you can observe your sample with the oil immersion objective. Then what you have to be careful is to not go back and put this objective on the oil. That's it.
I didn't notice this before.
Yeah. Another thing also to take into account is the objectives have two numbers. The first one is, for example, 63x is the magnification. And then there is another number next to it. It says 1.4 in this case. This is the numerical aperture. And the higher the numerical aperture, here for example, the 10x has, the other number is 0.30. So the higher the numerical aperture, the higher the resolution that it can achieve. That's also important because people sometimes think that the magnification is everything, but we were going to buy an objective which was 100x, and I was asking for prices and everything, and in the end they told me, but the numerical aperture is the same that you have. So we won't have better resolution just because we have more magnification. So the two numbers, the first one tells you how much you are magnifying, and the second number tells you about the resolution that the objective has. Okay, I think that's more or less everything about the objectives. And then the software.
Okay.
So, do you know how it works more or less, the confocal principle? No. Okay, so when you have a normal light microscope, like the ones we have in the other lab, this is the confocal. Yeah. When you have a normal microscope, you have your sample and you have white light, so light in all the colors of the visible spectra, the normal light, white light.
Sunlight.
Yeah, of all the colors, and then you can see either the light that is transmitted or reflected or anything. In this case, instead of having white light, we have a monochromatic light. So it's a light with one wavelength. Do you know what's wavelength? I don't know if you have studied this or not. No. Okay, so the light is basically like a wave.
Yeah.
And some colors vibrate with a higher frequency or a lower frequency. So the wave has like a bigger aperture or smaller. The white light is a combination of many different wavelengths. So you have the blue light, you have the red light, all the colors.
Yeah.
In this microscope, we only use monochromatic light. So it means it will only have one wavelength. We can have these wavelengths. Now it's not activated, but it says 633 nanometers or 561 nanometer down to 405 nanometers. So we can only use 1, 2, 3, 4, 5, 6, 7 colors. But it will be a very pure color. Instead of one white light with all the colors, it will be like in what is shown here. We will select only one color. Okay? And then I'm going to write here in the booking. Let's see if I have a pen around here. Okay, so the different molecules have an absorbance spectrum. No? If you go to the UV visible spectrophotometer, you usually have absorbance, and at different wavelengths, so different colors of the lights. At the beginning, for example, you don't have any signal, but depending on the molecule, it will absorb light at a specific color. No? For example, if it absorbs in the red, you will see it blue, the complementary colors and everything. So you won't see anything, and then, for example, you will have a peak of absorbance at a specific color. And this is the maximum absorbance at a specific wavelength. No? So this is the color at which the sample will absorb. So this is the color we need to use to excite the dye. For example, the dye we use for the proteins, I think is excited at 633. So we have to use this light to detect it.
So all the lights being extracted, being absorbed at that stage, like 633, well, being all absorbed by the fat or by the dye.
By the dye.
By the dye.
By the dye.
Okay.
Yeah. It's the dye. It's actually the dye that we use that absorbs the light that we are going to use, and then will emit fluorescence. So, for example, one molecule that absorbs here the light, it means that it takes some photons. The photons excite the molecule, so it goes to an excited state, and then at some point it has to go down back to the normal state. So it will emit another photon to go back to the normal state.
Okay.
And this photon is usually at a different wavelength. So the spectrum of emission will be, for example, this one. Then we will have the maximum of emission. This was the maximum of absorbance, and this is the maximum of emission. And this is controlled with this other set of filters. So basically, this is the lights we can use to excite the molecules, and these are the filters we can use to collect the light, and they will be different colors. Okay, so maybe we excite using a red laser, and then we collect the light in blue, for example.
Okay.
Okay?
Yeah.
So how do we turn on the different lasers? Here in configuration, you have different options. The laser, there are 4 lasers, and we had 7 colors. So it means that one of the lasers, which is actually the argon laser, can give 4 different wavelengths. And this laser is very sensitive. It has a shorter lifetime because it's more sophisticated, but on the other hand, it's more delicate. So if you use the argon laser, you have to have more precautions than with the other lasers. For your samples, I think we will only need these 2 lasers. So we just turn these ones on. One we will use for the dye that we will use for the protein, and the other one for the fat.
For the fat, okay.
Those 2 lasers. So you turn these 2 on, and then you go back to the other option, which is acquire. This is where we were when the software started. It automatically goes to acquire. You can always go back to configuration, and you can change things about the laser. Also here you have the objectives that we were talking about, the different objectives we have installed. But in this case, this microscope is automatic in the sense that if I change the objective, you don't have to come here and tell the microscope, I'm using the 10x, or it detects it automatically.
Okay. Did you have any other lenses?
Some other objectives.
Yeah.
For this microscope, no.
No. Okay.
No. But for example, in the other microscopes we have there, there's the optical microscope, the normal optical microscope. You have to tell him, I'm changing the objective because otherwise the scale will be wrong. When you have the image, the scale is automatic.
Come from here.
Yeah, so depending on the magnification you are using, you will have to have a different scale bar. In this case, that's automatic for this microscope. So if you change the objective, it detects it and it adjusts the scale automatically. So you don't have to worry about this objective option. Just lasers to turn it on and off, that's all. And then you go back to acquire. And then in acquire, you have to turn on as well the visible, because we have these two now activated because we have turned on the lasers. So we have two different options already. If we turn on the ergon, these 4 will activate. And if we turn the first one, 405, it corresponds to the UV.
Okay.
For the dice we are going to use today, these 2 should work.
Okay.
And then the power we usually use, we start around 20%, more or less, and if that's worked,
20%.
Yeah, of the power, because the higher the power you use, the more the lasers suffer, let's say. So you can always go to 80%, but then you will be pushing them more and they will last less. So if we can work around 20-30% is ideal. If your sample doesn't have enough fluorescence, maybe you have to increase. But as a starting point, we usually go to 20%.
For example, my digestion, there are some coagulations, right? I think it's outside is the protein, and inside is the fat.
We will see that. Yeah.
Is it possible to see inside? Oh,
Yeah.
you can see inside, really?
To some limits. It depends on how transparent is the sample, but that's the good thing about confocality. So the other difference between the normal optical microscope and the confocal microscope, is that the normal microscope, for example, you have here, I draw very badly, but let's see if I can show you. You have, for example, here your sample. So you have a light source, and then you will have light which is emitted from the sample in this direction, in this direction, in this direction, in this direction, in this direction. No? So in a normal microscope, you always have some parts in focus and some parts that are not in focus if it is not completely flat, because it's impossible to look at all the planes at the same time. So the confocal microscopes have what is called a pinhole, which is basically something to block all the out of focus light, and only the light that is in focus will go through the pinhole and be collected. And this other ray, for example, will impact here and will not be collected. So we will focus on one specific plane of the image. But then with the Z position, we can go up and focus here, and go down and focus here. So we can focus at different planes, and we can take images on the surface and a little bit deeper. So
a little bit of the sample, you mean?
Yeah, a little microns. You can penetrate microns inside the sample. Depending on the transparency of the samples, if it is really, really opaque, you won't see much inside, because the light has to go inside, excite the fluorophore, and then the emitted light has to come out. And if the material absorbs all the light, you won't see anything. But with protein gels, they are transparent enough to be able to penetrate a few microns inside. So then if you, for example, have a structure like this, and these are proteins
yeah.
and these other ones are fat,
yes.
If this won't be many microns, for sure. You will have space to go down and see inside.
Great, that's what I want.
Okay.
So, do we wait for something?
I'm just going to show you a couple more things in the software, and then we prepare the sample.
Okay.
What time is it? Okay, 3. when you have to leave, if I don't realize that it's 3:30, let me know. Yeah. Don't worry to interrupt or anything, because maybe I forget. So just tell me. Okay, where's the mouse? Okay, so then once we are in Acquire, we have these two options. Experiments is just where you have your project, let's say. So you can create a new project here in New and rename it. For example, e-home training, as an example. And then every image that you take will be inside this folder.
Okay.
So then you can save this project, and it will be saved with all the images that you have inside. It will be a file with an extension of .lif, which can only be opened with this software, but then you can export to TIFF using this software. I will show you how.
Okay.
And then once you have them in TIFF, you can open in any computer. But when you save the project, the .lif, you are saving all the images that are inside that folder.
In that folder, okay.
Yeah.
So I can create other folder.
You can create, for example, one folder per sample or one folder per experiment. That's up to you how you want to organize your images. And for example, you can create a new one, another one. You can then delete it if you want. Yes. And you can also, and this is very useful, open a previous experiment and use the same conditions that you used. For example, if I already know what conditions work for these two dyes that we are going to use, I can open an experiment in which I use those two and apply the same filters and lasers that I used. So next time you can use the same conditions.
It's a method, like it's like the running method saving this software. Running methods, like to remember all your settings.
Yeah. It has some metadata inside the file. Apart from the images, there is some metadata where all this information is stored.
Okay.
So if I open now, for example, one of these .lif, it is one project that I was working on last time. It's opening all the project, which has several images inside. It will appear here as a different project with, I took many images that day. This was my project, and these are the individual images that I have inside. So I can go through all the images that I took. And from here I can export into TIFF to use them in any other computer. But let's say here I used this dye for the fat. These are fat droplets. This was an emulsion in which I have milk and coffee. So the milk had some fat, which was stained with this dye. And these are the proteins, which were stained in the other color. These are two different channels. And I can also see the combined image. Hello. The combined image present here. Show overlay image. And here you can see the combination of the two colors. So you can clearly see where is the fat located and where is the protein located. And these conditions worked fine for me. So what I can do is just press here apply in this. And now look at the lasers and the filters. If I look apply, if I press apply, you saw that they changed.
Oh yeah, yes.
So I'm applying the same conditions that I used in my previous experiment. So if you want to image all your samples in the same conditions, you just have to, once you save your project, next time you can open it, select one of the images and press apply.
Okay.
And then you will automatically have the same conditions that you used the last time. So now that we have opened these conditions, I can close my project. Close experiment, this one. But the conditions remain. And then we select your project, and everything we do will be with these conditions. Now maybe for your samples we have to adjust a little bit, but it will be similar because I use the similar dyes, the same dyes.
Okay.
I think that's all. No, there's another thing that would be good to say now. So apart from experiments, that are stored here. You have acquisition, and here important things is the resolution. By default, when you turn it on, the resolution will be 512 by 512. But you can, if for example you are going to present this image in a poster and you want a very good resolution, you can increase the resolution if you want.
Oh, okay.
For example, if it is for a poster that you are going to print it big, I recommend this one, 1024 by 1024.
Okay.
And then you can also have
if it's on the paper.
Take it. If it is for publishing, take it with good resolution.
Okay.
You can always decrease the resolution later. It's better to have the good image.
How do you do that?
With image J or something like that, you can compress. Yeah. It is better to have good images if you intend to publish. If it is, for example, preliminary data only that you don't know if you are going to publish or not, it's not worth it. But if you are intending to publish or put them in a poster or something, use good resolution. So this is one of the things that is important to change. The other important thing is the zoom factor. So apart from the optical magnification that you can get with the objectives, let's say for example here we have 20x, we can further increase the magnification but digitally. If you put for example a zoom here, it will digitally increase the size, but the resolution is the same because we are using the same objective.
Yeah.
So it's always better to go up to the highest magnification optically if you can, and then if you need to increase, we can't go further because we don't have better objectives, then you can zoom in. But don't use, for example, the 5x and then put a zoom here. It's not worth it. You can use another objective. And the third thing that it's important to know here is about the line average and frame average. So, for example, you will see when we start scanning one of the samples, it is called confocal laser scanning microscopy because it's confocal, it has the pinhole, so it's always in focus. It's laser because we use lasers to excite, just to have one wavelength of light, instead monochromatic light. And scanning because instead of illuminating all the sample at the same time, like in a normal microscope, what it does is illuminate this small bit and then scan. So it goes like this. If you want to take all this image, it will be scanning like this.
Okay.
So line average is how many times it's going